Curve fitting is the process of finding a mathematical function that describes the relationship between measured variables. The observations really lie on a perfect curve because real data contains noise. The fitted curve captures the underlying trend and allows us to explain, interpolate, and predict. Once the relationship has been fitted, an input value can be mapped to a predicted output, including values that were not directly measured. Every curve fitting problem has 4 ingredients: measured data, a candidate model, residual errors, and an objective used to choose the model parameters. For a straight line fit, the predicted value is a plus bx. The residual is the measured value minus this prediction. Ordinary least squares chooses a and b to minimize s. The sum of the squared residuals. Squaring prevents positive and negative errors from cancelling. At the minimum, the partial derivatives of s with respect to a and b are 0. These conditions produce the normal equations. After expanding and rearranging, we obtain 2 simultaneous normal equations. Solving them gives the slope b as covariance divided by the variance of x, and the intercept r as y bar minus bx bar. Linear regression fits a straight line. It is fast, transparent, and often the best starting point. Polynomial regression adds powers of x. It captures bends, but a very high degree can overfit the data. Exponential and power law models describe growth, decay, and physical scaling. Nonlinear least squares fits models whose parameters cannot be isolated with simple linear algebra. So an iterative optimizer is used. Splines join low-degree polynomial pieces smoothly. They are flexible while remaining stable over a wide interval. Robust fitting reduces the influence of outliers. Regularization adds a penalty that discourages unnecessarily complicated models. The same observations can be fitted by several model families. A straight line misses the curvature, while a quadratic captures the broad pattern. A higher degree polynomial may follow every small fluctuation, including random noise. More flexibility is not automatically better. An underfit model is too simple and misses the real structure. An overfit model memorizes random fluctuations and may fail on new data. To choose complexity fairly, fit candidate models on training data and compare their performance on separate validation data or by cross-validation. Useful measures include mean absolute error, root mean squared error, R-squared, and information criteria such as AIC or BIC. No single score tells the full story. Residual plots can reveal bias, changing variance, missing curvature, and unusual observations. A real mechanical example is a vibrating mass attached to a spring and damper. A displacement sensor records how the motion decays after the mass is released. The governing equation contains mass, damping, and stiffness. Its underdamped solution is an exponentially decaying sinusoid. The white points are noisy displacement measurements. Nonlinear least squares adjusts the model parameters until the blue curve best follows these points. From the fitted parameters, an engineer estimates damping ratio, natural frequency, stiffness, and damping coefficient. These values help diagnose vehicle suspension, rotating machinery, buildings, and robotic mechanisms. Training a supervised machine learning model is a generalized form of curve fitting. Data enters a model, a loss measures error, and an optimizer adjusts the parameters. A practical example is battery health prediction in electric vehicles and phones. Capacity measurements are collected across repeated charge cycles. A fitted degradation curve estimates remaining capacity and forecasts when the battery may cross a replacement threshold. Modern machine learning models can use several inputs at once, including temperature, charge rate, and voltage history. The fitted function then becomes a surface in many dimensions rather than a simple line on a graph. The model must be tested on batteries it did not see during training. Predictions inside the observed range are usually safer than long-range extrapolation. In cloud systems, engineers fit response time against incoming request rate. The curve helps plan capacity and reveals when congestion begins. In algorithm analysis, measured running time is fitted against input size. Candidate curves help distinguish linear, n log n, quadratic, or exponential growth. In data science, time-dependent curves forecast product demand, network traffic, hospital occupancy, and energy consumption. Suppose a programmer benchmarks an algorithm at increasing input sizes. The white points are measured execution times. A linear model misses the accelerating growth, while a quadratic curve follows the measurements much more closely. This empirical fit does not replace mathematical complexity analysis, but it helps detect bottlenecks, compare implementations, and estimate practical resource requirements. The MATLAB program fits a straight line y equals ax plus b. It first clears the workspace, reads the x and y vectors, and counts the observations. For this example, x contains 1 through 5, and y contains the 5 measured values 2.1, 4, 6.1, 8.2, and 9.9. The dot operators are important. X dot squared squares each element, and x dot times y multiplies corresponding elements. The required sums are 15, 30.3, 55, and 110.7. These sums form a 2 by 2 system of normal equations for the slope r and intercept b. The coefficient matrix A and right-hand side B are passed to MATLAB's backslash operator. This is the recommended way to solve the linear system. For the supplied data, the verified slope is 1.98, and the intercept is 0.12. Therefore the best fit line is y equals 1.98 x plus 0.12. The earlier value 1.96 is a numerical typo. The plotting section first draws the experimental points as circles. Hold on keeps the same axes active, and the second plot command draws the fitted line. The red vertical segments are residuals. Least squares chooses the line that minimizes the sum of the squares of these vertical errors. In summary, the program resets MATLAB, reads the data, computes the required sums, solves the normal equations, evaluates the fitted line, and plots the measurements together with the model. For production code, also check that x and y have equal lengths, contain finite values, and include enough distinct x values to determine a line. A reliable curve-fitting workflow is to plot and clean the data. Choose plausible models, estimate parameters, inspect residuals, validate on unseen data, and interpret the result using domain knowledge. The best curve is not merely the one that hugs the training points most closely. It should be accurate, simple enough, physically meaningful, and reliable on new data.